Hello and welcome. This is the second video with chapter 26 on electric potential, and I want to kind of continue here and go through what is a source of electric potential, how that potential is created, and then what we can do with it once we have it. So first thing I want to do is kind of go back here and kind of show you the geometry here of potentials and field in general. What we see here is we see two charged electrodes. It looks like the rod here is positively charged. Okay, and so the rod is at a very high positive potential. The ball here, the little conducting sphere, it might be positively charged, it might be negatively charged, but all we know is that it's at a lower potential than the rod. So the rod is at a high potential, possibly because it's curvature, and the ball is at a lower curvature or lower potential. So what we see is that there's field lines, right? Those are the lines with the arrows. Those represent the electric field lines. The electric field, every location in space around these two charged electrodes has an electric field that's along a field line that starts at the positive rod and terminates on the electrode. And furthermore, we see that the equipotential surfaces, they almost morph from one shape to the next, right? And that's exactly what the dipole shape did actually as well. The dipole electric or equipotential surfaces kind of start in the shape of a circle near one of the point charges, and then it kind of morphs into an ellipse and then eventually a straight line, and then morphs back into a circle for the negative charge. This is kind of the same thing. So near the rod, we've got this equipotential surface. The closest one to it looks like, kind of an oblong ellipse. I mean, there's an equipotential surface actually on the surface of the rod that is the exact same shape. And so in this way, we're seeing how an equipotential surface kind of morphs in from one shape to the next. And this is in general what electric fields are going to look like. They're far too complicated to write down a formula for. And so we have to resort to these pictures and at the end of the day, approximations. Okay, so this talks about sources of the electric potential. Anytime you're able to somehow transfer electric charge, any way that we can transfer electric charge from one thing to the next, we're separating charge, and therefore there's a voltage between those two things. Okay, going back to the very first experiments we did in chapter 22, where we rubbed plastic on wool, right? The act of rubbing plastic on wool was separating charge, right? Now there's a negative charge on the plastic, positive charge on the wool. Now the plastic and the wool have a voltage between them. So there's a difference in electric potential between them. Okay, same with the silk and the glass, right? The glass now has a positive charge, the silk has a negative charge. So those now have an electric potential difference or voltage between them. And if we were to somehow not connect, but if we were somehow take some glass and some silk, separate them, and fix them in space, we would have the beginnings of a battery. Because what's going to happen in a battery is that there's something between the two terminals that has to create a separation of electric charge, and when you connect it to the other things, that charge is going to pass through those other things. Enter the charge escalator model. So the charge escalator model of an ideal battery is a model that says that the chemical reactions inside a battery are always going to be separating the electric charges between each other, right? So it kind of escalates this positive charge from a bottom plate to the top plate, leaving negative charge at the bottom. So you're always seeing some way to create a separation of electric charge and therefore an electric potential difference or voltage. In this chapter or in this course, we do not go into detail about the chemical reactions that underlie the sources of these potentials. It's a very fascinating topic, and an extremely interesting one, and a very important one. Modern smartphone batteries can run for days, actually, with a very low, very low transfer rate, because they have a ton of charge on them. And these smartphones and laptops require a lot of current, a lot of charge passing through them to operate, right, with the screens and with how the processors process all these different processes. And so these batteries, the chemistry behind how these batteries work is very interesting. The most basic one is an electrochemical cell, where two different solutions of maybe two different metals, one of them, they undergo what are called these reduction oxidation reactions. And in these reduction oxidation reactions, the one of the atoms loses electrons, and that causes the other atom to gain electrons in a more complicated terms. And that's how you're able to create a separation of electric charge. So these chemical reactions are the source of it. We don't go through the details of how these things work, but it's kind of interesting. And so the concept of an EMF is the critical idea to define the voltage of a battery. The EMF, the term stands for electromotive force, but it's not a force at all. The EMF of a battery is the amount of work that it does on a certain amount of charge. It's basically how powerful the chemical reactions are. So we're going to be referring to batteries and other sources of potential in terms of their EMF. Okay. Another remark about batteries is that in series, they just add together, right? Old electronic devices, like all these old little, pocket like games that I remember playing as a kid. Like if you plugged in a game, if you had batteries from an old Game Boy or something, I mean, it would require 4 batteries or 2 AA batteries or something. And so that means that if the thing requires 2 AA batteries, then it requires an EMF of 3 volts, right? It's a circuit that's designed with an EMF of 3 volts. And so that circuit is going to have 2 1.5 volt AA batteries in series with one another. No one ever does batteries in parallel. So batteries in series is the only thing we're going to use. And so now this gets us into the important topic of capacitance. So imagine if you have 2 different electrodes. Okay, capacitance kind of answers the question, if you have 2 electrodes and they're different shapes, and you connect either of them to the terminals of a battery, how much charge are you going to get on those electrodes? These electrodes could be any shape. And what you'll see is that maybe from the very beginning, you don't have a specific way. So what if you started taking measurements? Let's say you had let's say you had 2 electrodes of different shapes. Maybe one is shaped like a square, like a plate, and the other one is shaped like a spherical ball. And you connect both of them to the terminals of a battery. And what is, let's say the battery is a 3 volt battery, and you find that it has a certain charge, say 1 coulomb or something. It's too much, but just for sake of argument. Okay, capacitance says that if you add a second battery, if you double the voltage, you double the amount of charge that's on those electrodes. And if there's 1 coulomb of charge, that means that the electrode connected to the positive terminal has positive 1 coulomb of charge. The electrode connected to the negative terminal of the battery has minus 1 coulomb of charge. Again, 1 coulomb of charge is too big, but just for argument's sake. So if you add 2 batteries, then each one would store 2 coulombs of charge. And if you connect 3 batteries in series, then there would be 3 coulombs of charge. And so capacitance reflects this linearity, this proportionality between the increase of charge stored on the electrodes versus the voltage applied across them. You double the voltage, you double the charge. You triple the voltage, you triple the charge. You cut the voltage in half, you decrease the charge by half. So that is how we define the capacitance of those two electrodes. Now it turns out that the type, okay, in this formula at the bottom here, we have capacitance, and the equal sign with 3 dashes means definition. So the capacitance is defined as the ratio of the charge stored on the plates divided by the voltage across them. Okay, this equality here with the formula epsilon naught A over D, that is a specific formula for two plates of equal area that are separated by a distance D, and they're parallel with one another. It turns out that the capacitance of different shapes electrodes will affect this final formula. So this epsilon naught A over D is specific to just two equal area plates that are separated by distance D that are parallel. If the plates were not the same area, we'd get a different formula. If the electrodes were not plates, we would get a different formula. And the key to getting the different formula is recognizing how to find the potential between the plates from their electric fields that they create. And so you might have a homework problem where you have to find the electric potential difference between two electrodes that are not, easy plates. So like we say, capacitance is the effect of the surface area of two electrodes. In a very deep mathematical sense, you could actually, if you take two surfaces, no matter what their shapes are, if you take two surfaces, you can define the capacitance between those surfaces just from these formulas here. Now the unit of capacitance is coulombs divided by volts. And that's technically coulombs squared over joules. So that defines the farad. 1 farad is defined as 1 coulomb squared per volt. It's far too big of an actual number, and so most capacitors typically use microfarads and nanofarads. Sometimes even smaller ones use picofarads, actually. And so, yeah, we have this relation between the charge stored on the electrodes, which they have the same electrodes. The electrodes have the same charges as Q equals C delta P. That's a common formula that you'll see. And here you see some typical realistic capacitors, what they look like. Actually, most industry capacitors and ones you'll see in the labs, yeah, here's different arrangements. There's some that are actual plates, some that are kind of these kind of arrangements. Some capacitors are often thin strips of metal that are like two thin strips of metal with a layer of material in between them kind of rolled up. That's another example. Keyboards, right, old desktop keyboards are basically, dozens of capacitors, right? Each key on the keyboard has a capacitor below it, and then when you make a key stroke, right, pressing down that key kind of changes the distance between those plates, changing the capacitance, and that voltage registers, in the processor as being a stroke of, say, the D key or something. Also, touchscreens. Many touchscreens are what are called capacitive touchscreens, and so when you touch the screen, that changes the capacitance of the layers in between. Touchscreens have a small electric field on them, and so touching them changes their capacitance as well. But the important relation of, I'm going to skip this because what we see is how you charge a capacitor. I'm going to skip this real quick, though, and say that, well, the symbol of capacitors is these two dashed lines. And we have here two basic circuits, actually. We have the battery. Okay, we'll introduce the symbol for the battery in chapter 28. But on the left-hand side, we have three capacitors, what are called wired in parallel. And then on the right-hand side, we have three capacitors wired in series. Parallel means that the charge that's leaving the battery has a choice to go to any one of those three capacitors. Series means it only has one choice to go through. The current only goes through one loop. And so when we're talking about how much charge a battery delivers to a network of capacitors, we have to kind of reduce the circuit, so to speak. And it turns out that if you go through the derivation in the textbook, you'll see that the total charge delivered by the capacitor to these two capacitors in series is the same as if the battery was connected to a single capacitor with capacitance equal to the sum of the two. And so in that way, we say that the equivalent capacitance between two or more capacitors wired in parallel is just their scalar sum. Right? Capacitance is a number. It's just a scalar, and in fact, it's a positive number numerical quantity, scalar. Non-negative scalar, just like mass. What about when they're wired in series? Well, it turns out, if you follow the derivation of the textbook, it turns out that the total charge delivered by the battery here is equal to the same as if it was a single capacitor, but that capacitance is not the sum, it's actually the inverse of the sum of the inverses. So you see that formula there, that like 1 over C1 plus 1 over C2, all to the -1 power. And so the equivalent capacitance for N capacitors wired in series is this formula, which really we could get rid of the -1 subscript and just write on the left-hand side 1 over C equivalent. And then so those are the two formulas that you'll be using a lot when we're talking about the how to analyze a circuit when you have capacitors with more than one different arrangements. Like if you have 3 capacitors, it's possible to connect them all in series. It's possible to connect them all in parallel, but it's also possible to connect them, say, where one is in parallel with the battery and the other 2 are in series in parallel with the battery. So we get different circuit diagrams that you see in your homeworks. Okay. Anyway, I think this is actually a good stopping point for this video. So this has been the introduction to capacitance, and there's some examples in the textbook of how to deal with those. In the final video for chapter 26, we'll go through how energy is stored in a capacitor and see kind of a really interesting new topic about new way to interpret the electric field. So stick around for that. As usual, thanks for your time, and we will see you back here for the third video. Take care.